Real numbers. Introduction. We have studied different types of numbers in earlier classes such as natural numbers, whole numbers, integers, rational numbers, and irrational numbers. Let us recall a little bit about rational numbers and irrational numbers. Rational numbers. These rational numbers, which can be written in the form of p by q, where both p and q are integers and q is not equal to 0. All rational numbers can be written either in the form of terminating decimals or non-terminating repeating decimals. Irrational numbers. These irrational numbers cannot be expressed in the form of p by q. These include numbers like √2, √3, √5 and mathematical quantities like pi. When these are written as decimals, they are non-terminating, non-recurring. Example: √2 equals to 1.4142135 and so on. Pi equals to 3.14159. These both numbers can be located on number line. Therefore, the set of both rational and irrational numbers together are called real numbers. These numbers, we can show them in the form of a diagram. Diagram of real numbers. Rational numbers, integers, whole numbers, natural numbers. Irrational numbers. Which of the following rational numbers are terminating and which are non-terminating repeating in their decimal form? 17 by 18. Solution. Given 17 by 18 to find these numbers in terminating or non-terminating. Let us divide denominator with numerator. As 18 is greater than 17, put decimal point in quotient. As 8 is repeating, this is a non-terminating. Represents repeating and it also called as bar. So, 17 by 18 equals to 0.944 bar, which is non-terminating. 15 by 16. Solution. Given 15 by 16, so 15 by 16 equals to 0.9375, which is terminating. Solve given rational or irrational numbers. √24. Solution. √24 equals to √4 into 6 equals to √4 into √6 equals to 2 to the power of 2 whole to the power of 1 by 2 into √6 equals to 2√6. Therefore, √6 is an irrational number shown below. There, we will consider the numbers between 5 by 10 and 10 by 10. As 5 by 10 equals to 1 by 2 and 10 by 10 equals to 1, so the rational numbers between 1 by 2 and 1 are 6 by 10, 7 by 10, 8 by 10, 9 by 10. Simplifying further, we get 3 by 5, 7 by 10, 4 by 5, 9 by 10, and so on. 3 1 by 3 and 3 2 by 3. Solution. To find the rational numbers between 3 1 by 3 and 3 2 by 3, take averages of both the numbers. Equals to sum of numbers by 2. Equals to 3 1 by 3 plus 3 2 by 3 divided by 2. Equals to 3 into 3 plus 1 by 3 plus 3 into 3 plus 2 by 3 divided by 2 equals to 9 plus 1 by 3 plus 9 plus 2 by 3 divided by 2 equals to 10 plus 11 by 3 divided by 2 equals to 21 by 3 into 2 equals to 21 by 6 equals to 7 by 2 equals to 3 1 by 2. Exploring real numbers. In this section, let us explore real numbers. We know that natural numbers are also in real numbers. So, we will start them. The fundamental theorem of arithmetic. We have seen that all natural numbers except one can be written as a product of their prime factors. Example, 3 equals to 3, 6 as 2 into 3, 253 as 11 into 23, and so on. 1 is neither a composite nor a prime. We think that there may be a composite number which is not the product of the powers of prime. Example, let us factorize a natural number. Let us take some large number, say 1,63,800, and factorize it as shown below. Solution. From below factorized, 1,63,800 as 2 into 2 into 2 into 3 into 3 into 5 into 5 into 7 into 13. So, 1,63,800 equals to 2 cube into 3 square into 5 square into 7 into 13. When we write it as a product of power of primes. For another example, 12 crores, 34 lakhs, 56,789 can be written as 3 square into 3,803 into 3,607. Therefore, 3,803, 3,607 are primes. Therefore, this leads us to a conjecture that every composite number can be written as the product of powers of primes. Now, let us try and look at natural numbers from the other direction. Let us take any collection of prime numbers, say 2, 3, 7, 11 and 23. We multiply some or all of these numbers, allowing them to repeat as many times. We can produce infinity, many large positive integers. 2 into 3 into 11 equals to 66. 7 into 11 equals to 77. 7 into 11 into 23 equals to 1771. 2 into 3 into 7 into 11 into 23 equals to 10,626. 3 into 7 into 11 into 23 equals to 5313. 2 cube into 3 into 7 cube equals to 8232. So, if we multiply all these primes in all possible ways, we will get an infinite collection of composite numbers. This gives us a fundamental theorem of arithmetic which says that every composite number can be factorized as a product of primes. Actually, it says more that given any composite number, it can be factorized as a product of prime numbers in a unique way, except for the order in which the prime number occur. Theorem. Fundamental theorem of arithmetic. Every composite number can be expressed or factorized as a product of primes. And this factorization is unique apart from the order in which the prime factors occur. In general, given a composite number x, we factorize it as x equals to p1, p2, so on, pn, whereas p1, p2, and so on to pn are primes and written as ascending order, that is, p1 is smaller than p2, p2 is smaller than p3, and so on is smaller than pn. If we use the same primes, we will get powers of primes. Once we have decided that the order will be ascending, then the way the number is factorized is unique. Example: 1,63,800 equals to 2 into 2 into 2 into 3 into 3 into 5 into 5 into 7 into 13 equals to 2 cube into 3 square into 5 square into 7 into 13. While this is a result that it is easy to state and understand, it has some very deep and significant applications in the field of mathematics. We have already learned how to find HCF and LCM of two positive integers using the fundamental theorem of arithmetic in earlier classes. This method is also called as prime factorization method. Example: find the HCF and LCM of 12, 18 by the prime factorization method. Solution: 12 equals to 2 into 2 into 3 equals to 2 square into 3 to the power of 1. 18 equals to 2 into 3 into 3 equals to 2 to the power of 1 into 3 square. Therefore, note that HCF 12, 18 equals to 2 to the power of 1 into 3 to the power of 1 equals to 6, which is the product of the smallest power of each common prime factor in the numbers. Therefore, LCM 12, 18 equals to 2 square into 3 square equals to 36, which gives the product of the greatest power of each prime factors in the numbers. From above example, you might have noticed that HCF 12, 18 into LCM 12, 18 equals to 12 into 18. In fact, we can verify that for any two positive integers a and b, HCF a, b into LCM a, b equals to A into B. This result to find the LCM of two positive integers. If we have already found the HCF of two positive integers. Example: consider the number 4 to the power of n, where n is a natural number. Check whether there is any value for n for which 4 to the power of n ends with the digit 0. Solution: for the number 4 to the power of n to end with digit 0 for natural number n, it should be divisible by 5. This means that the prime factorization of 4 to the power of n should contain the prime number 5. But it is not possible because 4 to the power of n equals to 2 to the power of 2n. So, 2 is only prime in the factorization of 4 to the power of n. Since 5 is not present in the prime factorization, so there is no natural number n for which 4 to the power of n ends with digit 0. Rational numbers and their decimal expansion. In this section, we are going to explore when their decimal expansions of rational numbers are terminating and when they are non-terminating, repeating. Let us consider the following terminating decimal forms of some rational numbers. 0.375 equals to 375 by 1000 equals to 375 by 10 to the power of 3. 1.04 equals to 104 by 100 equals to 104 by 10 to the power of 2. 0.0875 equals to 875 by 10,000 equals to 875 by 10 to the power of 4. 12.5 equals to 125 by 10 equals to 125 by 10 to the power of 1. 0.00025 equals to 25 by 1 lakh equals to 25 by 10 to the power of 5. We see that all terminating decimals taken by us can be expressed as rational numbers whose denominators are powers of 10. Let us prime factorize the numerator and denominator and then express the simplest rational form. 0.375 equals to 375 by 10 to the power of 3 equals to 3 into 5 to the power of 3 divided by 2 to the power of 3 into 5 to the power of 3 equals to 3 by 2 to the power of 3 equals to 3 by 2 into 2 into 2 equals to 3 by 8. 1.04 equals to 104 by 10 to the power of 2 equals to 2 to the power of 3 into 13 by 2 to the power of 2 into 5 to the power of 2 equals to 26 by 5 to the power of 2 equals to 26 by 5 into 5 equals to 26 by 25. 0.0875 equals to 875 by 10 to the power of 4 equals to 5 to the power of 3 into 7 by 2 to the power of 4 into 5 to the power of 4 equals to 7 by 2 to the power of 4 into 5 equals to 7 by 2 into 2 into 5 equals to 7 by 20. 12.5 equals to 125 by 10 equals to 5 to the power of 3 by 2 into 5 equals to 25 by 10 equals to 5 by 2. 0.00025 equals to 25 by 10 to the power of 5 equals to 5 to the power of 2 by 2 to the power of 5 into 5 to the power of 5 equals to 1 by 2 to the power of 5 into 5 to the power of 3 equals to 1 by 4000. Do you see a pattern in the denominators? It appears that when the decimal expression is expressed in its simplest rational form, then P and Q are co-prime and the denominator has only powers of 2 or powers of 5 or both. This is because the powers of 10 can only have powers of 2 and 5 as factors. Let us conclude. Even though we worked only with few examples, you can see that any rational number which has a decimal expansion that terminates can be expressed as a rational number whose denominator is a power of 10. The only prime factors of 10 are 2 and 5. So, when we simplify the rational number, we find that the number is of the form P by Q, where the prime factorization of Q is of the form 2 to the power of n, 5 to the power of m, and n, m are non-negative integers. Thus, in this way, we can write our result as formally. Theorem. Let x be a rational number whose decimal expansion terminates. Then x can be expressed in the form P by Q, where P and Q are co-primes and the prime factorization of Q is of the form 2 to the power of n, 5 to the power of m, where m, n are non-negative integers. Solution. You are probably wondering what happens the other way round. That is, if we have rational number in the form P by Q and the prime factorization of Q is of the form 2 to the power of n, 5 to the power of m, where n, m are non-negative integers, then does P by Q have a terminating decimal expansion? So, it seems to make sense to convert a rational number of the form P by Q, where Q is of the form 2 to the power of n, 5 to the power of m, to an equivalent rational number of the form A by B, where B is a power of 10. Let us do some examples. Examples. 25 by 2 equals to 5 to the power of 3 by 2 into 5 equals to 125 by 10 equals to 12.5. 26 by 25 equals to 26 by 5 to the power of 2 equals to 13 into 2 to the power of 3 by 2 to the power of 2 into 5 to the power of 2 equals to 104 by 10 to the power of 2 equals to 1.04. 3 by 8 equals to 3 by 2 to the power of 3 equals to 3 into 5 to the power of 3 by 2 to the power of 3 into 5 to the power of 3 equals to 375 by 10 to the power of 3 equals to 0.375. 7 by 80 equals to 7 by 2 to the power of 4 into 5 equals to 7 into 5 to the power of 3 by 2 to the power of 4 into 5 to the power of 4 equals to 875 by 10 to the power of 4 equals to 0.0875. 1 by 4000 equals to 1 by 2 to the power of 5 into 5 to the power of 3 equals to 5 to the power of 2 by 2 to the power of 5 into 5 to the power of 5 equals to 25 by 10 to the power of 5 equals to 0.00025. So, these examples show us how we can convert a rational number of the form p by q, where q is the form of 2 to the power of n, 5 to the power of m, to an equivalent rational number of the form a by b, where b is a power of 10. Therefore, the decimal expansion of such a rational number terminates. We find that the rational number of the form p by q, where q is a power of 10, will have terminating decimal expansion. So, we find that the converse of theorem 12 is also true and can be formally stated as: theorem, let x equals to p by q be a rational number such that the prime factorization of q is of the form 2 to the power of n, 5 to the power of m, where n, m are non-negative integers. Then x has a decimal expansion which terminates. Non-terminating, recurring decimals in rational numbers. Let us consider rational numbers whose decimal expansion are non-terminating and recurring. Once again, let us look at the example to see. Let us look at the decimal conversion of 1 by 7. 1 by 7 equals to 0.142857 and so on, which is a non-terminating and recurring decimal. Here we notice that 1, 4, 2, 8, 5, 7 is the repeating in the quotient. Notice that the denominator, that is 7, is not in the form of 2 to the power of n, 5 to the power of m. Therefore, from the above example, we can formally state in other theorem. Theorem, let x equals to p by q be a rational number such that the prime factorization of q is not of the form 2 to the power of n, 5 to the power of m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating repeating. Solution. From the above discussion, we can conclude that the decimal form of every rational number is either terminating or non-terminating repeating.